Hello, sir. I'm Balaganesh, and today I'll be giving my video PPT on the topic of making a queue using the 8085 simulator. So this is all what I'm going to be covering in today's presentation. First, I'm going to be talking about what is a queue. Then I'm going to be showing you a possible visualization of the queue, and that will give us a little bit of motivation about how we can make the 8085 simulation for the queue. So then after that, I'll show the programming that I have written in 8085 itself. And last, I'm going to show you the results of my simulation. So first of all, what is a queue? A queue is a specific kind of data structure in which you can store multiple elements, but you can add and remove one element at a time only. And the first element that goes in is the first element to come out. So that is known as FIFO, first in, first out. The elements will be added to one end of the queue, but then when you remove them from the queue, they will come out from the other end, so that the first element that entered the queue will also be the first one to leave the queue. So the three basic operations that must be provided by the queue data structure are enqueue, dequeue, and check if empty. So these things will become clearer when I discuss the animation in the next slide. So this is this is a visualization that I have made myself for a queue. So this these boxes depict a block of memory, and you can see there is a pointer referring to the head and another pointer referring to the tail of the queue. So those so now both the head and the tail are pointing to the same memory location. That is an indication that the queue is empty in this case. So let me show what happens when you do start doing operations on this queue. You enqueue. What happens when you enqueue 08H? Let's see. So as you can see, the value 08H is written into the head pointer, and at the same time, the head pointer gets incremented so that it gets prepared to write data into the next memory location for another enqueue operation. So then if I do another enqueue, the same thing happens. FFH gets written into this memory location and the head pointer moves ahead. Now let me show you what happens when I do a dequeue operation. So here what will happen, the value in the tail pointer will get returned, and the tail pointer will get updated to go to the next memory location, so that you can do a dequeue. When you do a dequeue again, then the same procedure gets repeated. Now let me enqueue um, another byte of data. So then the same thing happens. New data gets written and the head pointer moves ahead. Then then if I do a dequeue, then it will return FFH and the tail pointer will move ahead. If I do a dequeue again, the tail pointer will move ahead and this memory location, this value will be returned. Now you can see that the head and the tail pointer are again pointing to the same memory location. So that means the queue is empty. So what happens if I call dequeue on an empty queue? Ideally, that needs to generate an error because there's literally no meaning in removing an element from a queue which has no elements in it. So we need to check for this kind of a condition as well. So this animation, I believe, will give some motivation into how we will write the 8085 program for this. So as I said, the above idea will be used to write the program in the 8085 simulator. Here, what I'm planning to do is I'll use the BC register pair to store the value of the head pointer of the queue and the DE register pair to store the tail pointer. So, and also I'll be using the HL register pair to write the results of the DQ operations into different memory locations. So I can show them as results of the program. So let me describe the code for all the main functions that I'll be using. So first one is the enqueue function. What it does is it enqueues the data from the accumulator into the queue. So remember that the BC pair is a head pointer. So it stores the value of the accumulator in the memory location referred to by the BC pair. And then the BC pair the BC pair gets decremented, and we return from the function. Then, so this NQ function was fairly simple. The DQ function is a little bit more complicated because we need to check whether the queue is empty. So, so before I do the DQ operation, I make a call to another function called isEmpty. That is a function that I'm going to be discussing on the next slide. It will set the zero flag if the queue is empty. Otherwise, the zero flag is reset. So if the zero flag is set, I immediately return by using this rz command, return if zero. So a DQ operation does nothing when the queue is empty. Then then if the queue is not empty, we'll reach this line of code. So what happens? I load the data from the tail pointer into the accumulator. So I've used the DE pair. Remember, I'm using the tail pointer, not the head pointer, to DQ, and then I decrement the tail pointer so that I'm ready to DQ the next byte of data, and then I return from the function. So now let me talk about the isEmpty function. It's a function that checks if the queue is empty and sets the zero flag in such a case. So as I said, the queue will be empty if the BC and the head and the tail pointers are the same. In our case, that means the BC and DE pairs must refer to the same register pair, the same memory location. So first we need to compare the upper bytes of data. So I've moved the data from B into A and then compared that value with D. So now if both these upper bytes of these pointers are equal, then I need to compare the lower bytes to check whether the pointers are in fact equal or not. But if they are different, then I can immediately return, because if the upper bytes are different, the two pointers will be different only. So that's why I have written RNZ, a return if not zero. Then I have done then I have done a similar procedure for the lower bytes of the pointers. So I've moved the C register into A and compared it with E. And now if both of these are equal, the zero flag will be set, and that is a confirm that will happen only if both the bytes are the same, and that means the queue is empty. And then it will return, but with the value of the zero flag state is saved. This can be used. This needs to be used in the later code. So then finally, I've got another function that stores the data from A into the memory unless the Z flag is set. So here I'm using the Z flag as a kind of a, error checking thing. So if the zero flag is set, I've written RZ, so it will automatically return and not store any data. So if the zero flag is not set, then the value of the accumulator will get stored in the memory, and the memory pointer will get incremented so that we can store the next byte of data as the output, and then I return from the function. So now I'll come to the main program. So here, let's see. So here I have initialized the B and D register pairs with the value 2055H. So, so both the head and the tail are pointing to the same memory location. So that is an indication that the queue is empty, as I said. So, so now I will do the same operations that I described in the animation before. So first I enqueue the data 08, then I enqueue the data FF over here by storing each of these into accumulator and calling enqueue. Then if I want to store the results of DQ operations in memory, I need to initialize my memory pointer. I set it to 2070H. Then I call DQ. I call DQ. Now the data that I have DQ'd is in the accumulator. So then I call store data, and that will store the data from the accumulator into the memory. Then I enqueue one more byte of data, 04H. Then I call DQ. Then I call DQ once more. Then I call DQ once more. So up till now, just see what has happened. I've called NQ 3 times and I've called DQ 3 times. So at this stage, the queue is in fact empty, isn't it? So then the question arises: what happens if you DQ from an empty queue? But that, of course, I have discussed in the earlier slides. What will happen if the queue is empty? So, so if I call dequeue and call store data in this case, in fact, there will be no dequeue operation performed because of the setting of the zero flag, and even the store data function will not do anything because it will return if the zero flag is set. And then I halted the program. So after this, let me show you the results of running the program. So yeah, after running the program, this is what you see here. So in these memory locations, you can see the data that was written to the queue. First 08, then FF, then 04. It was stored in this order, if you remember in the animation. And if you look at the BC and DE pairs at the end of the execution, you can see that the, the BC and the DE pairs are both referring to memory location 2052, and that has no data, and that is an indication that the queue is empty. Now the three DQ operations show that the first data byte that was written 08 will get DQ'd first, and the second data byte that was written will come second, third one will come third. That is what is meant by first in, first out. And by the way, this 2070 is where the the output of the DQ operations was stored. So yeah, and also the last DQ operation did not do anything. It did not move the BC or the DE pointers. They are still pointing to 2052 only. So that means the error checking was also working in the code. So with that, I come to the end of the video. Thank you for watching.